So this is going to be a quick explanation of systems of equations when you're doing graphs. When you're talking about a system of equation, we're talking about two or more equations and a point that would satisfy both of those. So in most cases, your graph is going to look like this one here on the left, where you have a pair of intersecting lines. In this case, there is one solution that works for both of the two equations, the two lines, and that solution is the point where they intersect. So for this particular graph, we are talking about the point -2, 1, and that would be the solution. That's the value of x and y that make both equations true. The second possible outcome here is to have a set of parallel lines like here in the middle. If you have a set of parallel lines, that would mean they have the same slope but different y-intercepts. Since they will never intersect, we would say they have no solution. There's no ordered pair that they share in common. The third possible outcome is this third graph here with the infinite solutions. This is a set of coincidental lines. This means they're the same line. They have the same slope, they have the same y-intercept, and so every single point that works for one would also work for the other equation. So they have infinite solutions. Both of these two scenarios, if you notice, they do have the same slope. So if you have a situation where you have the same slope on an equation, you are either going to have no solution or infinite solutions. If the slopes are different, you should end up having intersecting lines, and therefore you would have one solution. So let's see what this looks like. If you're given two equations in slope-intercept form like these, y equals -2x plus 6 and y equals x plus 3, then you would graph the two lines. So if we start at 6 and decrease by 2 and run 1 there, so there's the line for the first graph. And if we start at 3 with a slope of 1, so rise 1, run 1, there's our second graph. And then we would be looking for this point of intersection. So the solution to this system is at the ordered pair 1, 4. This one is similar in the sense that they're both in slope-intercept form. So we would start at -2 with a rise of 2 and a run of 1. So there's the first line. And then you do want to be careful as you're graphing these. You want to make sure that you are very neat with your work and that your ordered pairs are in the right spot and that you do your line correctly, because if you don't, then you're not going to see the intersection where it's supposed to be. So this one here intersects at 2, 2, and that would be the solution to this system. Now sometimes your equations will not be in slope-intercept form, and at that point you could graph it using the x and y-intercepts, or you could convert them. So if I take 2x minus y equals 2 and I go to convert it to slope-intercept form by subtracting 2x, and then I'd have to divide by -1, so y is positive, that would make it 2x minus 2. Then I could graph it from slope-intercept form. For the second equation, if I have -2x plus y equals 4, then I would simply need to add 2x to both sides. So y equals 2x plus 4. And then you may have noticed already that these do have the same slope, which means that they're never going to intersect. And so instead of saying an ordered pair, we would simply say that there is no solution to this system. These two lines will never cross. On this one, again, they're not in slope-intercept form, so you could either get the x and y-intercepts and draw the line, or you could solve it to slope-intercept form by getting y by itself. So if we isolate y, the first equation ends up being 3 minus 3/4 x. So if I start at 3 with the slope of -3/4, that would be my first line. And then with the second equation, if I have x plus 2y equals 2, subtract x, and then divide by 2. So that would give me 1 minus 1/2 x. Which would look like this. And so the point of intersection on these occurs right there at 8, -3. So that would be the solution to this system. Okay, so if I tried this one, if I have 2x plus y equals 6, and I subtract 2x, so y is equal to 6 minus 2x, then I could start at 6 and go down 2 with a run of 1. Looks like this. Better. And then the other one is already in slope-intercept form, so it starts at -2 and also has that slope of -2. And so this is one where we are again going to have no solution. They have the same slope, different y-intercepts, and so they're parallel lines. So they'll never cross. And then I skipped E on accident, so let me go back. On this one, if I were to graph the first line, which is at -3 with a slope of 3. So it would look like this. And then if I go to write my second equation in slope-intercept form, I would get y equals 3x minus 3, which is the same line. And so if I were to graph it, it would just end up right on top of this one. They're the exact same line, and so this would be infinite solutions. They share every point in common, and so they have every solution, infinite of them. And that's how you would solve these systems, by graphing. Now, graphing's not the only method. We will learn substitution and elimination method as well, which sometimes those are easier than graphing, but graphing is a viable option. Unless, I personally would not use a hand graph, like graphing by hand, if it's going to intersect at like a decimal value. That would be very hard to judge from a graph that you do by hand. Of course, you could use technology on a graph, and that would help as well. So